Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on analytical dynamics or classical mechanics, chapter Lagrangian dynamics, lecture number 9, in which I will solve some problems on Lagrangian dynamics. Now we solve a problem. Problem is, discuss the motion of an insect which travels at a uniform rate on a uniform heavy rod which is turning about a fixed end. Now we solve this. Let us consider 2a be the length of the rod OA with mass capital M. The rod is turning about a fixed end O. Let at any time t the inclination of the rod to the vertical, OZ be the vertical, inclination of the rod to the vertical OZ be theta, and angle which the vertical plane, this is the vertical plane A prime through the rod makes angle phi with x axis. It is spherical polar coordinates. In spherical polar coordinates, the coordinates are r, theta and phi. Similar to this, here we get here theta with z axis and the vertical plane through the rod with x axis be phi. Let m be the mass of the insect. Insect is traveling on the rod with uniform speed u. Let m be the mass of the insect and u be its uniform speed. Let at t equal to 0, it starts from the middle point G of the rod. The middle point G of the rod is at a distance A from the fixed end O. Because length of the rod is 2a, so middle point will be at a distance A, small a. Since speed of the insect be u, means uniform speed u, so in time t it will travel at a distance u multiply t. So after time t the insect will be at a distance from the fixed end O will be a plus ut. A be the distance of the middle point of the rod, and from this point the insect starts its journey with uniform speed u. So the distance of the insect after time t from the fixed end O will be a plus ut, and the x coordinate will be x equal to a plus ut sin theta cos phi. Y coordinate will be a plus ut sin theta sin phi. Z coordinate will be a plus ut cos theta. Now differentiating this x, y, z with respect to t. Here dx by dt is x dot equal to, firstly differentiate this term with respect to t. A is constant, so remains only u sin theta cos phi, u sin theta cos phi. Then we differentiate sin theta with respect to t. Differentiation of sin theta is cos theta and theta dot, cos phi remains same. Then we differentiate cos phi differentiation of cos phi is minus sin phi. So here we have written minus sin phi, then phi dot, and other terms remains same. Similarly, y dot equal to u sin theta sin phi plus a plus ut cos theta theta dot sin phi plus a plus ut sin theta cos phi phi dot, and z dot equal to u cos theta minus a plus ut sin theta theta dot. This is equation number 2 and this is equation number 1. Now we take x dot square plus y dot square here. Here we see that in x dot we have u sin theta cos phi. Here u sin theta sin phi whole square. U square sin square theta cos square phi, u square sin square theta sin square phi. We take common u square sin square theta, so remains cos square phi plus sin square phi. Similarly, we get other terms here. Here we get u square sin square theta, this is 1. Here sin square phi plus cos square phi 1. So remains a plus ut whole square cos square theta theta dot square. Here we see that this term phi dot term and this term cancel out, and here we also see that this term and this term also cancel out. So remains here u square sin square theta, here a plus ut whole square cos square theta theta dot square, and here we see that 2 u a plus ut sin theta cos theta theta dot common cos square phi plus sin square phi, this from these two terms. So we get this term and a plus ut whole square sin square theta phi dot square, this. So we get this term. Now z dot square equal to, we get this term here z dot square a minus b whole square, and then x dot square plus y dot square plus z dot square. Here we see u square sin square theta, here u square cos square theta. So we take common u square, remains sin square theta plus cos square theta, that is 1, that is here u square. Now here we take a plus ut whole square theta dot square common, and here only remains cos square theta plus sin square theta 1. So here theta dot square a plus ut whole square. Here this term plus and this term minus cancel, only remains this term here. So from these two terms we take common a plus ut whole square, here remains theta dot square, here phi dot square sin square theta. This is number 3. This is the velocity of square of the insect, that is v1 square is this. This is the velocity square of the insect. Therefore kinetic energy of the insect at time t, let this is T1. Therefore T1 equal to half mass of the insect multiply velocity square. This is the velocity square. This is number 4. Let P be a point on the rod at a distance r from the fixed end O. Let at time t the coordinates of point P be x, y, z. Therefore, in spherical polar coordinate, x equal to r sin theta cos phi, y equal to r sin theta sin phi, z equal to r cos theta. differentiating, we get x dot. Here r is constant. Differentiation of sin theta is cos theta. Theta dot cos phi remains same, plus r sin theta. Differentiation of cos phi is minus sin phi. Phi dot. Similarly, y dot equal to, here r differentiation of sin theta is cos theta. Theta dot sin phi remains same, plus r sin theta remains same. Differentiation of sin phi is cos phi. Phi dot. And z dot equal to r differentiation of cos theta is minus sin theta. Theta dot. This is number 6. Now velocity square of the point P will be v2 square, that is equal to x dot square plus y dot square plus z dot square, and by calculating this we will get r square theta dot square plus r square sin square theta phi dot square. The mass of the rod of length dr, total mass of the rod is capital M and total length is 2a. Therefore, m by 2a be the mass per unit length. Then for length dr, mass will be m by 2a multiplied dr. Therefore, kinetic energy of the small element dr of the rod will be half mass of this portion and velocity square. This is the velocity square. Therefore, kinetic energy T2 of the whole rod, this rod OA, will be integration of this part half m by 2a, and we write this part, then dr, and integration limit 0 to 2a. Here we may take common r square. So we take other term free from r, and so we take it out from the integration because this integration is with respect to r. So here only remains integration limit 0 to 2a r square dr. Integration of r square equal to r cube by 3, limit 0 to 2a, and putting this value we get here 2m capital M by 3a square under bracket theta dot square plus sin square theta phi dot square. This is the kinetic energy of the rod. Therefore, kinetic energy T of the whole system will be T1 plus T2. T1 be the kinetic energy of the insect and T2 be the kinetic energy of the whole rod. This part is kinetic energy of whole rod and this part is kinetic energy of the insect, and we get equation 8. Now we find the potential energy V of the whole system. This potential energy is given by minus V. Minus V is written in the sense that reduction in potential energy, because any point is under the fixed point O. So potential energy is reduced downwards. So minus V equal to capital mg a cos theta. Here the center of gravity of the rod is at a distance a from the fixed point O, and the gravitational force acts on the rod at the center of gravity of the rod, and this center of gravity is at a distance a from the fixed point, and vertically downward we take its projection, that is a cos theta. So mg be the force multiply displacement a cos theta. So this is capital mg a cos theta. Similarly, the distance of the insect be a plus ut, and its projection along z-axis is a plus ut cos theta. Gravitational force acts on the insect will be mg multiply displacement. Force multiply displacement is the work done, and this work done is reduction in potential energy, and plus constant. Now we take the partial differentiation of t with respect to theta dot. Here t be this in 8, and if we differentiate this with respect to theta dot, we will get equation 10. Similarly, we take partial differentiation of t with respect to theta. We differentiate this partially with respect to theta, we will get this value 11. Now we take minus of partial derivative of v with respect to theta. Here with respect to theta, this cos theta will be minus sin theta, and this cos theta will be minus sin theta. So we get equation 12. Now Lagrange's equation for variable theta will be d by dt partial derivative of t with respect to theta dot minus partial derivative of t with respect to theta equal to minus partial derivative of v with respect to theta. Here d by dt, we put the value partial derivative of t with respect to theta dot number 10 here. Then we put the value of partial derivative of t with respect to theta 11 number here, and this is minus partial derivative of v with respect to theta 12 number right side, and we take here common theta dot and remains other terms. Here we take common sin theta cos theta phi dot square and remains other term here, and right side we take common g sin theta, and this is number 13. Now we find partial derivative of t with respect to phi dot, and we get this under bracket 4 by 3 m a square plus small m a plus ut whole square bracket close sin square theta phi dot. This is number 14, and partial derivative of t with respect to phi equal to 0 because t does not contain phi explicitly. Similarly, v does not contain phi explicitly, so partial derivative of v with respect to phi equal to 0. This is 15, this is 16. Now Lagrange's equation for the variable phi will be d by dt partial derivative of t with respect to phi dot minus partial derivative of t with respect to phi minus partial derivative of v with respect to phi. We put these values from these equations 14, 15 and 16, and we will get this equation. Integrating this, we get this term equal to constant. This is equation 17. By taking the value of phi dot from here 17, we use this value in 13. Here we have phi dot square. So in 13 we get equations involving only theta variables, and we may find the value of theta from 13. Then again taking value of theta we put here we put, and we get value of phi dot, that means we may get the value of phi. So we may get the value of theta and phi, hence we get the value of theta and phi. So the equation of motion is completely determined, because with the help of theta and phi and the distance of the insect from fixed point is a plus ut at time t, and here we get theta and phi. So we may find the x coordinate, y coordinate and z coordinate of the insect completely. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.